All right, hi everybody, it's Mr. Dan, and I'm going to teach you guys today some tricks you can use ideal gas law for. This might be useful for you as you're doing your some calculations for your labs, and maybe give you some ideas if you haven't gotten too far on that yet about what you can do. So let's check it out. Ideal gas law. What we're going to do is talk about how to calculate density and mass using the ideal gas law. And here you can see the equation for it up here. Okay, so before we go too far, let me make myself a little bit smaller. Okay, so we want to relate density and mass of a gas to the ideal gas law. So do you know of any way that you can relate density, which is mass divided by volume, to anything in our equation? So our equation, maybe you notice that it already has volume in it, okay, right there. And so that's great, right? That's going to help us along the way in relating these to our law. So let's start then instead by looking at mass specifically in our equation. So mass is not listed anywhere in there, so what can you relate mass to in the equation? Pressure, is there any way to do that? Well, pressure is a measure of force, right? It's a pushing force per unit of area. And so yes, force is mass times acceleration. So mass is involved in that, but this is just for a single particle when we're talking about force. A single particle or a single object exerting its force on something else. We are interested in the cumulative effect in that when we're talking about pressure. Okay, so gas pressure, there's many particles that are applying a force, and that force is different for each particle based off of how fast it's moving and how big it is, something like that, right? So pressure and mass aren't really going to relate very well for us. So what about volume? Yes, of course, volume and mass are related. It's called density. And so we know what density is, right? Mass divided by volume. And here's a couple of different ways that we can measure that. And essentially, as that number for density decreases, it starts to look more like this box here on the left, where there are less particles in a given amount of space. Higher density, more particles in a given amount of space. So whatever you're measuring it with, the bottom line is as that number decreases, it becomes less dense and there's less stuff in that area. So as we go from solid to liquid to gas, the density decreases. All of these three shapes right here are showing us the same amount of matter, but it's being spread out a lot more as we change the shape and the state of matter here. Okay, so how about R? R is our ideal gas constant, so that's not going to work out. These numbers never change, right? The number does change depending on which unit of pressure we're using, but once you put that into our equation, like this value never changes. That's why it's called a constant. Okay, temperature then. Can we relate temperature and mass together? Well, temperature is the average kinetic energy. And maybe you guys remember this. We made this a long time ago. And this showing the relationship of kinetic energy and temperature. Okay, so as all those particles are moving up, their kinetic energy is increasing as their temperature increases. Kinetic energy is 1/2 mv squared is the equation for it, and so mass again is involved, and we'll come back to that in a second. This image here just shows us the three different units of measurement for temperature: Kelvin, Celsius, and Fahrenheit. These are the three most common, at least. But we can't use this one either because, again, temperature, this is a cumulative effect of all the particles in the substance, right? It's the average kinetic energy. So we could maybe use the kinetic energy of a single object or a single particle to relate it to mass, but not for the billions upon billions of molecules in a gas sample. So then, moles, yes. N, definitely We can use that. It's in our equation there. What do we know about moles? So I don't think I ever showed this to us, but I know some of you have seen it. This graphic shows us a relationship between mass, moles, and molar mass. And what you can do is you can solve for any one of these three by doing certain calculations. So if you want to solve for moles, you would take mass and then divide it by the molar mass. If you want to solve for molar mass, you could take mass and divide by moles. And if you want to get to mass, you could take molar mass times moles, and I'll get to that. So here, N is moles, M is mass, and that should be a little n. That's a mistake there. Little n is moles, little m is mass, and big M is molar mass. So this equation right here, right, N equals M over M, is our equation to solve for moles. So we can use this. Now we've got a direct relationship between mass and our equation. So what we want to be able to do is we want to be able to find the mass of a gas sample if we have a certain set of data to go along with it. So how can we do that then? This is the real point. We can do this then starting with our original equation here, okay? PV equals nRT, where we have pressure times volume equals moles times our gas constant times temperature. So what we want to do then is we want to substitute in this little m, mass divided by molar mass, right? This right here, we want to substitute that in for our moles. So that's going to look like this, okay? So the equation is just going to change a bit, where instead of n, we've got this mass divided by molar mass. So it fits into the whole equation there. Okay, so once we do that, if you want to specifically find the mass of your gas, if you know the pressure, volume, and temperature, then you just take this and you're just going to isolate for m, little m there, mass, which is going to change the equation to look like this. And this can be useful for us. Oh, better move my head there. There we go. So this is useful. Move. There we go. This is useful if you know the contents of your gas, like what it is. Is it nitrogen? Is it oxygen? Is it a mixture of some kind? If you know the contents of your gas, then you can find out what the mass is if you have these other pieces of information. And it's pretty easy to get that information. Pressure, you could look at a barometer. Temperature, you can look at a thermometer. Volume, you can look at whatever the container size is. But you might not know exactly how much you have in there in terms of mass. So we can solve for it using this process right here. So that's great. What else can we do with this? Maybe we know the mass, but we don't exactly know what. Let's see. Where can I put myself? I'll put myself up here. I know this is weird, right? Okay, so maybe we want to find the molar mass, and we'll talk about why we might want to do that in a second. But so what we're going to do here is we're going to take this equation from here where we solve for mass. We did that substitution up here, and we're just going to isolate for m instead, which is a pretty easy process. Okay, so just kind of shuffling around the variables, multiply, divide on both sides. Okay. And it's gonna look like this instead. So molar mass is gonna be mass times R times temperature divided by pressure and volume. So why would you want to do this? Well, maybe you know the mass and all the other stuff, but you don't know exactly what the gas is. So if you have the molar mass, you can you have a better chance of identifying what that substance is. So this can be very useful for us. In a real practical sense. Okay, last thing, density. We can find the density of a gas as well. And this would be helpful for us in trying to figure out like what the behavior of a gas might be, what might happen when we introduce it to other gases or other substances. So to do this, starting off, I'm going to have to move myself again here. Actually, I think I'm okay. We know that density is mass divided by volume. Okay? So how can we apply this to what we've shown so far? Well, take a look. It's up there. Can you see where mass divided by volume is up here? Right? Here's mass divided by volume. So we'll just isolate for that again. Okay, so we got to move P over here and RT over there. Okay, so divide by ideal gas constant, divide by temperature, multiply by volume, or I'm sorry, multiply by pressure. And that's going to isolate that M over V for us to look like this. Okay. And M over V is density, so we can just substitute that term in, D, or density, and we're going to end up with this right here, okay? So here we've got three different things we can do using the ideal gas law, aside from the other stuff, right? I mean, just at the start, we can use ideal gas law. We can use ideal gas law to solve for any of these four unknowns or these four variables if we have the other information along with it. Now we can find out a bit of extra information as well just using this old stuff that we learned, goodness, last semester, I think. So that's a long time ago, but it's still useful for us. So we can substitute that in and find mass, find molar mass, find density. And this might be useful for you now based off of whatever experiments you're doing at home. For some of you, maybe you're doing something where you're using fire, there's some sort of combustion going on, and you're trying to apply temperature to your situation. Well, maybe you want to apply something like a change in moles or mass to your calculation and your conclusions instead. So think about how you might be able to use this in your experiment. If you have questions about that, let me know. You guys can look for a homework assignment to follow this up. And I guess that's all I've got for you guys today. So good luck on this, and I hope to see you soon.